Hello everyone, our presenter today is Dr. Samuel from University of Derby, UK. Dr. Samuel received his PhD from the Chinese Academy of Science, or CAS, in pattern recognition and intelligent systems. And he has been an associate professor at the university, at Shenzhen Institute of Advanced Technology, CAS, and the Shenzhen University of Technology, CAS. And now he's a senior lecturer and the leading investigator on University of Derby, UK. Welcome.
Good afternoon, everyone. I'd like to express my thanks to Dr. Yudao and everyone that made this seminar possible, as well as all the attendees. It's indeed a great honor for me to have the opportunity to share my research papers with each and every one of you on the advances we have made in our group in the recent years when it has to do with developing some robust control systems for rehabilitation robots, or perhaps assistive robots. So, my talk for today about divided into 5 different parts. Of course, the last part would be the kind of question and answering session, of course, discussion. So he's done a bit of introduction, but I have just 1 or 2 slides to further tell you about my educational background and how I got to where I am currently at the University of Derby. And after that, I would also share an overview of my research and talk about part of the things we've been doing, which constitutes research progress 1 and as well progress 2. And also, I have a couple of scholarly accomplishments I'd also like to share with you all. So, about my educational background. In 2009, I obtained my bachelor's degree in computer science from Kogi State University in Nigeria. In 2014, I got my master's degree in computer science as well, but with specialty in expert systems from the Federal University of Technology in Nigeria as well. Between those times, I had interest in web technology and database management, so I got some professional certification for Oracle University in California. While in 2018, I obtained my PhD degree in pattern recognition, like he said, from the University of Chinese Academy of Sciences in Beijing. And also, just last year, I got some professional qualifications as well, one from the MIT that has to do with building optimized machine learning models for solving critical problems, and also another certification from the University of Colorado on managing teams, research, and all that. So in terms of my work experience, after graduation in 2009, I joined Aptech Technology, which focuses on computing education and software development. So in 2010, I joined Hands-On Institute of Information Technology, which does similar things like Aptech. And from 2010 to 2014, I joined High Technology Research and Development Group, first as a systems analyst, then later as a senior software engineer. While in 2014, I joined the government agency, the State Information Technology Agency, as a program analyst. And I had to resign my job and went for my PhD from 2014 to 2018. After completing my PhD in 2018 from the University of Chinese Academy in Beijing, I joined the Shenzhen Institute of Advanced Technology as a postdoctoral research fellow, working on upper limb prosthesis and rehabilitation robot for stroke patients and the like. Then, upon completing my postdoctoral research fellowship program here, I was promoted to the rank of associate professor until early this year, when I joined the University of Derby as a senior lecturer. So, just to give you an idea of where University of Derby is located in the UK. It's located in Derby, Derby is a city in Derbyshire, and Derby itself is surrounded by Leicester, Nottingham, and Loughborough. And Derby is, of course, famous for a number of things, which includes the industrial presence. I mean, the presence of a lot of automotive industries in Derby. Just like the Rolls-Royce, I'm sure some of us might know Rolls-Royce. Rolls-Royce has its headquarters in Derby. And of course, there are a lot of attractive things as well that you could see around Derby. So if you are visiting Derby, you're highly welcome, and I'll be glad to show you around. To begin with, my vision as a researcher or an educator is to constantly innovate AI-based technology, especially in two different fields, solving critical problems in two different fields, which include the rehabilitation technology or robotics, intelligent rehabilitation robotic systems, as well as intelligent decision support systems. For the intelligent rehabilitation robotic systems, I'm interested in approaching it from two different perspectives. The first is the muscle-computer interface, and the second part is the brain-computer interface. But my talk today, because of the time limit, he's told me I have about 45 minutes, right? I would focus on the muscle-computer interface aspect. That being said, I would like to share some of the things my group has done in this area, beginning with one of the works we did recently titled Deep Transfer Learning Model based on spatial temporal driven scholograms for precise decoding of motor intention of severely impaired stroke patients. Limb dysfunction is a common challenge faced by stroke survivors, and this affects them in various ways. For example, they can hardly grasp objects, meaning they easily lose their grasping function. Sometimes also, depending on the level of severity, they can hardly sense objects even when they grasp such objects. And because of their situation, the loss of the motor function, they could hardly cope with daily life activities. I mean, stroke patients. Therefore, they mostly need support from people around them. And in an attempt to rehabilitate this category of people back into the society, different kinds of technologies have been developed in the time past, which I have in my next slide here. For example, we have the physiotherapy-based approach, whereby the physiotherapist tries to study the stroke patients and understand the level of motor impairment. And upon that, the physiotherapist try to design some sort of physical exercise and help the stroke patient to engage in such exercise, hoping that after some time, the lost motor function will be restored. So this is the first approach. The second is the robot assisted therapy. I mean, this kind of technique for rehabilitating stroke patients, robotic systems such as exoskeletons are designed in such a way that they can help stroke patients perform certain kinds of exercise automatically with little or without the interference of a professional, healthcare professional like the physiotherapist. And this kind of technology is especially important in middle to low income countries. Of course, it's also important or relevant in high income countries. And the reason why I talked about middle to low income countries is that when you look at the ratio of those having stroke patients, the ratio of stroke patients to physiotherapists, the margin is really wide when we go to middle and low income countries compared to high income countries. So we also have the virtual reality based approach, which tries to kind of motivate stroke patients to engage in some kind of gaming activities. But the goal is to help them, like to motivate them to play those gaming activities, and in a way their motor function could be restored after a long period of time. We also have the mirror therapy and motor imagery training. But of all this approach, we are more interested in the robot assisted therapy. And there are a number of reasons to that. One of the reasons is that for biosignals such as EMG that could be picked up from the muscles of these patients, the signal is usually generated between 20 to 200 milliseconds before the actual movement is initiated. So what that means is this: if we are able to decode the movement intention of the stroke patients between that time, it means we already know the task, the upper limb task that the patient wants to perform. So we can code that decoded movement on the controller of the exoskeleton, such that the exoskeleton can help the patient to perform that task. This is one thing. Another interesting thing here is that depending on the level of impairment, we might be able to, we can estimate the level of impairment of the stroke patient. And with such estimation, we can decide the level of force that we need to provide to actually help that patient perform the task in the right way, as accurate as possible. So that's what I have here. The myosignal, the myoelectric signals usually is usually picked up between 20 to 200 milliseconds. It means we have some time to be able to do the decoding. And with that, once we decode the movement intention and be able to estimate the level of force needed, which correlates with the level of impairment, we can provide a very good robotic training that is specific in this context, adaptive to individual stroke patients. Going forward, in order to decode the movement intention of the stroke patients, pattern recognition schemes, various kinds of pattern recognition schemes have been proposed at the time. But of course, this is the general pipeline of the pattern recognition scheme. We try to pick up the signals via electrodes, surface electrodes, or even invasive. But these days, in the recent years, attention has shifted to surface electrodes, and there are a number of reasons why most people want to work with surface electrode. So we pick up the signals from the surface electrodes, try to do some signal pre-process, clean up the signals like filtering and all that, just to ensure that we get the information that is needed to be able to estimate or decode the actual movement intention of that patient and feed that pre-processed signal into the machine learning algorithm that does the decoding or characterization or classification, depending on what you want to call it. And at this stage, there are two different approaches: traditional machine learning approaches and the deep transfer or deep learning based approaches. We are particularly interested in the deep transfer learning. And the reason is because we don't mostly have large set of data for training this kind of model. So that's why we're interested in looking at transfer learning models that have been built using millions of exemplar data and try to adapt such models with few modifications and with the few data sets we are quite convinced that we might be able to get a model that would be good in decoding the movement intention. So these are some of the reasons why we went this way. And for a typical deep transfer learning models, there are three popular input representation to date. Some would want to use the raw signal, the time series representation. Some would transform the time series representation of the signal into spectrogram by performing the short time fast Fourier transform, which is also, this is also the time frequency representation. Some would want to use the CWT, continuous wavelet transform approach, to take this into the image, the scalogram images. While these are both time frequency representation, CWT seems very fast or much faster than this, and it gives higher resolutions. So we decided that this might be a good way for us to go, because one of the reasons is this guy is very fast. There is no need to take the data from the time domain to frequency domain, while this takes it from time domain to frequency domain first, which takes time. So we decided that scalogram might be a good way to go in this respect. However, from our previous investigation, we did found that the spatiotemporal based information associated with the muscle are quite important in helping to characterize the movement intentions of amputees, which we did previously. So we wanted to see if that spatiotemporal representation could also help in characterizing the limb movement intention of stroke survivors. So we felt we might want to propose spatiotemporal representation as input to our deep transfer learning model, rather than just using the scalogram, which has been popularly used till date in literatures. So therefore, this formulated the basis for this study, I mean the objective. Our objective here is to optimally characterize the motor intent of severely impaired stroke patients. For stroke patients with mild impairments, it might be relatively easier to decode their movement intention. And the reason is that they still have the ability to perform some kind of task, unlike the severely impaired stroke patients. So this is our goal. So to realize this, we aim to develop a spatiotemporal based scalogram as input to a transfer learning model and implement this method across different wavelet functions, which includes the three standard wavelet functions, which include the Morse, armor, and bump. And also apply this method to decode the limb movement intent of severely impaired patients, and also compare this method with the traditional approaches in literature. So having said that, we had to perform an experiment where we recruited severely impaired stroke patients and placed a total of 64 electrodes on their forearm muscles, their impaired side, and set the equipment's sampling frequency to 1024 hertz, and also designed up to 22 different classes of upper limb movements, which we actually instructed them to perform after training them on how to perform each. And they did that, performing each of those 22 classes of limb movement for 6 seconds with 6 repetitions. And yeah, we did some signal pre-processing and segmented the data into active and rest state for each of those movements. and did data windowing as well, and applied the spatiotemporal representation. STD means spatiotemporal descriptor. We constructed that based on the pre-processed data, and used some popular metrics to quantify the decoding output of our model in comparison to existing models in literature. Well, this is the framework of the spatiotemporal descriptor. As you can see, we have 5 different parts, or you would say subcomponents here. The first part here is the pre-processing, where we applied a 50 Hertz notch filter to knock off the power line noise from the signal, and did extracted signal within the frequency of 20 to 500 Hertz. Several literatures have proven this, that for EMG signals, the frequency that is most relevant in characterizing the limb movement lies between this range. So we did that. And we apply the windowing. These are the windowing parameters I mentioned in the previous slide. And did extracted the energy content from the data. That's the second part. The third part, we got the spectral information, which are all these parts. And the fourth part here, we try to calculate the force, estimate the force with which each of those severely impaired stroke survivors perform those 22 classes of movement. And this is like an aggregation of all. And then we have the representation that went into the deep transfer learning model. If you're interested in this, we've actually published a couple of articles with this representation. I'm interested in sharing this with you, and we can as well discuss this further after now. So this is like a representation of the whole pipeline, where we got the raw signal, we did some pre-processing. This is the spatiotemporal representation. Based on the spatiotemporal representation, we try to apply the C probability to generate the what? Scalograms that goes into the deep transfer learning models. And after the whole process, we have the movement intention being decoded. Like I mentioned previously, we did this using 3 different wavelengths, which is the Morse, Armor, and Bomb. And these are like the parameters of the network. And these are some of the results we got for this study. For individual subject analysis, we actually did recruited 5 severely impaired stroke patients. We were hoping we could recruit up to, let's say, 20 for the pilot study. But unfortunately, even though we had some stroke patients signed up for this, but they couldn't turn up for one reason or the other. So we had to work with this for now. And if you look at this result, this is the training and this is the validation session. You would realize that the STD-based CWT, scalogram-based, generated based on this and fed into the deep transfer learning models, actually performed much better than the traditional approaches for both the training and both the testing. That's the summary we got here. And going forward, we wanted to see, we're also interested in looking at this across all the stroke patients, not on individual basis and see. And we also found that for both the training and the testing session, all the spatiotemporal based scalograms, you know, this guy, and this yielded much better decoding outcome compared to the traditional approaches. And we're also interested in checking this phenomenon across all the individual classes of limb movement to probably know if the accuracies across all classes are quite better than the traditional method. So we did that. And if you look at the diagonal value, I'm afraid the values might be too small for you to see. If you check the diagonal values for the proposed approach, we decided to use AMO here because it seems to perform best among the three different wavelengths. For AMO, our proposed method, this is the traditional approach, you would find out that all of the diagonal elements have higher values than that of the conventional approach. And that brings me to some conclusions here. We found that the use of spatiotemporal based representation in generating scalograms would help in better characterizing the limb movement intents of severely impaired stroke patients. And in fact, we were able to get increments in this range. And we hope that we could further investigate this. That's why I have some things to do in the future here. This data set is relatively small. We hope we could work with more data sets. I've been able to acquire a number of data sets for TBI patients, traumatic brain injured patients who have challenge with performing upper limb movements. So we would like to do that here as well. We also got some amputees recently data sets, which we would also want to further validate this to be sure that it works better on a broad range. Also, we're interested in looking at other deep transfer learning models, whether this result could be repeated using other deep transfer learning models, and yeah, also use some real-time metrics. So these are some of the things we hope to do, and we already started doing some of them. So that's the first part of my talk that relates to stroke. This second part relates to amputees. As you know, or as we may know, that amputation is a serious challenge for those affected. Just like stroke, amputees could hardly cope with daily life activities that requires their arm function. And the number of amputees globally has been reported to be around 5 million. And there was a report from the World Health Organization several years ago that the trend would continue to increase. I mean, as the year progresses, we would most likely have more people with upper limb amputation. So it's important to invest or work on technologies that can help this set of individuals, be able to perform simple and complex daily life activities that requires their hand function. So in this regards, various kind of prosthetics have been built in the time past. Different kind of prosthetic have been developed, myoprosthetics. But the state-of-the-art myoprosthetics has rarely made it to the clinic or even commercial outlets. And there are a number of reasons for that, which I would talk here. So therefore, with these challenges in view, my group is interested in investigating confounding factors that has actually hindered this technology from making it to the clinic or even commercial outlets. And not just stopping at the stage of investigation. We are mostly interested in trying to understand why and try to develop solutions that would help circumvent these challenges and then make this technology move to the next level, which of course, their clinical applications or even commercial, at the commercial level. So in this regards, there are various kinds of confounding factors. The first I listed here is electrode shift. It's a big problem. It has been well investigated. Electrode shift, I'll try to explain quickly. Electrode shift simply means when you don the prosthesis on the hand of the amputee, the position of the electrode might likely shift during usage. And such shift, for example, when you fit the prosthesis, electrode 1 can be here. During usage, it might slide either up, down, forward, backward. And such shift would lead to degradation in the quality, sometimes, of information that could be picked from the muscles. So this is a problem. So we have the cross-user model adaptation. What this means is that most of the studies till date focus on training a particular machine learning model. For example, using my data for training and testing. The model works perfect, but in practical deployment, that model is expected not to be used only for myself, but for other guys. So when you try to deploy that built model, the model that has been built with my data on other subjects, you would most likely see drop in performance. And the reason for that is simple, because the characteristics of my muscle or the signal generated from my muscle would most likely be different from the characteristics of the EMG signal generated from the muscles of others. So sorry. Yeah. So that's the second one. Then the muscle contraction force variation. For example, think about it. I'm trying to grasp an object, right? I can modulate my muscle with higher force, with low force, and moderate force, right? Each of these 3 different contraction levels, sometimes called maximum voluntary contraction, would differently affect the signals generated. And it's been shown that this would also affect their characterization. And in a way, also it has influence on the controllability of the prosthesis. Arm posture changes, time would not permit me to explain all. Mobility of subject is also a big problem, because most of the studies that have been done till date would ask individuals or amputees, whether able-bodied individuals or amputees, to sit down in the laboratory and perform the task. But in reality, the prosthetics is not only used while they are sitting, right? You use your arm even when you go around. So we did investigated some time ago that mobility would actually affect the usage of the prosthesis. So we are more interested in looking at these 2 together. What will the combined impact of these 2 factors look like? The muscle contraction force variation and mobility of subject on the characterization of the limb movements of amputees, and as well the impact of these both factors on the prosthetics itself. So that formed our research question here. So with that being said, we formulated an hypothesis, and the hypothesis says alteration in EMG signal patterns from the dual impact of muscle contraction force variation and mobility of subject may influence the decoding rate of individual targeted limb movements. We said may because we don't know, as at the time we were doing this. May or may not. So, well, we had to go further to investigate this by designing an experiment that allows us to take both factors into consideration. First, mobility of subject. We considered 4 different scenarios. We have each of the amputee performed specific classes of limb movement while they were sitting, while they were walking on a level ground, while they were ascending the stairs, and while descending the stairs. So that captures the mobility scenario. While for the other aspect, which is the variation in muscle contraction force, we asked them to perform in each of these scenarios the same set of limb movements, but with different level of muscle contraction force. High is 80% of the maximum voluntary contraction, while the moderate, 50% of the maximum voluntary contraction, and the low is 30% of the maximum voluntary contraction. And this is like the experimental circle. Trial 1, they had to take rest to avoid muscle fatigue. Trial 2, they take rest. Trial 3, like that, keeps going, like a representation. Having said that, we did pre-process the data, did segmentation, did some feature extraction, and also did 2 different kinds of analysis: intra-scenario analysis and inter-scenario analysis, just to be able to test our hypothesis, and used some popular performance metrics for machine learning models. And these are some of the results we got. What happens here is that this A represents the result for sitting, for walking on a level ground, ascending the stairs, and descending the stairs. So now, in each of these 4 scenarios, what we did was to train the machine learning model here, using data from low force level as the training to build the classifier, and used a combination of data from low, moderate, and high to test the classifier. What we did here is to train with low, but test with what? Low, moderate, and high also for the working scenario. So we did the same thing for all of the 4 scenarios. Interestingly, you would see when we trained with low and tested with concatenation of the 3, this is the result. When we trained with moderate and tested with concatenation of the 3 for sitting, when we trained with high and tested with concatenation of the 3. So you would see that generally, for each of the 4 scenarios, the moderate force level would help to generalize better than the low and the high. You can see the trend here. And more interestingly, our method is the invariant TDD. Could help us minimize the impact even much better for sitting, walking, ascending, and descending. So this is like the summary using the classification error metrics. We try to also use other metrics, which is the Matthew correlation coefficient, which is also a very good metric from literature. And we found that our method also could help us achieve the same thing across all the 4 scenarios. Don't forget, this is intra-scenario analysis. The next slide, we also try to look at the inter-scenario analysis. And what we did here is to train the machine learning model using the training data from low and excluding that low components, testing with moderate and high. Here, train low, test with moderate and high across force level and across all scenarios, and across all subjects. Same thing here. We trained with moderate, tested with what? Low and high across all the 4 scenarios. Same thing here, and this is like the mean. And we found out that our method for the inter-scenario as well, our method could give better performance. And we went further to look at the individual decoding accuracy under this condition. In comparison to existing methods, we found that our method, with the exception of just the wrist supination movement, we could have almost 90% accuracy, which was far better than what was reported in study till date. And we wanted to see the PCA analysis in 2 dimensions, the separability of this of this method, and we found that the classes could be obviously separated using this. And we went further to do some real-time experiment, comparing our method with the most two performed method here. This is the proposed method for the precise cylindrical grasping test. PCG means precise cylindrical grasping test, which I would play for you to see. Please note here, we took the muscle contraction force variation into consideration. If you observe the last part, which is the proposed, compared to the first two existing approaches, the amputee could better control the prosthetics, which helped him to perform the task more accurately, but not just more accurately, and even more timely. You will see the time it takes task. So with the proposed method, he's done. You can see this guy is struggling to. So these are some of the things we found from the practical implementation of this approach. We are still trying to design some kind of sockets in here that would help us to test the mobility scenario instance. So that's one. And apart from the precise cylindrical grasping test, which I showed in the previous slide, we are also trying to see if the prosthetics could be used with the proposed method to manipulate other objects, which includes square of various shapes. You can see there are some round objects like balls as well that we're designing here. So these are some of the things I wanted to share with you, the progress we are making. And we are also trying to look at the cross-user model here, at user adaptation. Because what happens here is that we build the model for specific individuals, more adaptive. And when we try to use that same model for other amputees, the performance went down significantly. So these are some of the things we are trying to see how we can resolve this problem. And it's a big problem in the machine learning community globally. We are also working on some some solutions on resolving electrode shift currently in my group. So these are some of the recent publications, related publications in our group. And these are some of the scholarly accomplishments we have made recently. And if you have any questions, discussions, I'm happy to entertain them. I'm as well happy to learn from you all. So thank you. So I like to acknowledge the School of Computing and Engineering, University of Derby, and also the Center for Neural Engineering, Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences, for their support in my projects. Thank you.
Questions?
Thank you for the talk. It's very interesting. I sort of have two related questions mostly about the experiments and sort of how you go about training these models, particularly in terms of, so I guess the first part is, how do you actually, I assume there's some kind of supervised learning going on.
Supervised.
How do you actually, and what's the complexity involved in actually determining what the person, what the action is based on the input signals. Like what does the data set look like? How accurate? What kind of movements are there that you're trying to evaluate? Because it could be, rotate left, but maybe there's more complex movements within that data set. So how do you separate them out, or is that the train? And the second part of my question is, because you have, it seems like you have some humans involved in some of the training. So for example, with one of the experiments you talked about, you asked the people to sort of apply force at 3 different levels. So, and I imagine that that is not the same for every person, and maybe across the experiment, the strong force, it changes a little bit differently. So how do you cope with that?
All right, thank you. Let me begin with that. For the force level, for the variation in force level, this was one of the things we wanted to investigate here, and not just investigate this, but also try to provide a solution to this problem. And we found that the spatiotemporal representation of the muscles could help extract robust features that would be invariant to the force levels, regardless of whether you're using high force level, moderate force level, and low force level. And this was the thing we showed, that across all the force levels, whether low, moderate, or high force level, I can put up the slide. Sorry, just a second. Whether moderate, so whether low, moderate, or high across scenarios, we wanted to make sure that we have a method that can generalize better, that is robust regardless to whatever force level you use. And that's why we have compared our method, and we found that with our method, although you can achieve 100% accuracy, but it's much better, the one in black, it's much better in terms of robustness to variation in force level.
See, okay.
So
yes, yeah, that makes sense. Thank you. And then the first part about
okay.
Training data.
Well, for the training data, what we did was that for the different tasks you saw, like the precise cylindrical grasping, of course, each of those subjects needs to perform the task again and again, and the data collected during this process is used to train the model. And we anticipate that the model would be robust enough to be able to recognize the different kinds of gestures. Or
Do you categorize, do you have like a set number of gestures that you train on?
oh yes, for this study.
And it's just everything has to be one of those.
Yeah, for this study we have, probably I didn't talk about it. Yes, sorry, just a second. I have that. Yeah, I think somewhere. We have 8 amputees, 7 classes of movements.
Okay, I understand. Okay.
And we have put the representation, we have represented them here, but yeah. This means hand close, hand open, wrist extension, wrist flexion, wrist pronation, wrist supination, and no movement.
Okay, thank you.
It's a question regarding for stroke patients.
Okay.
You said at the beginning that your data set was kind of full and that you were willing to have more data. Do you think that the time for the training of the model will scale exponentially with like more patients due to the fact that like the data is rich and like all the processing, the pre-processing, and all the pipeline can take messages. So that takes time. Do you think that with like many more patients, the training time will be scaling probably?
Well, in terms of your question, of course, if we have more patients, it will take more time. So it will take more time to build the model. But what we are actually looking at is trying to accomplish a cross-user model, which I talked about in here, whereby we can just, for example, if we have 100 stroke patients, we hope we can build a model using this data sets, and that model would be able to work well for every other individual. Whether the model has seen that individual's data or not. We're just interested in having all kinds of possibilities, maybe stroke data from stroke patients with different characteristics, not necessarily the same.
Yeah, thanks very much for the talk. I'm wondering, so I imagine, let's say someone had an amputation 10 or 15 years ago, their ability to, I suppose, use those muscles in the same way might be a little, say, less strong than someone who's just had a recent amputation. Is this something that you noticed in your data? Is there ways to sort of deal with that?
Yes, thank you for that question. And I must say, you're very correct. Because if you, especially if these categories of individuals, I mean the amputees or the amputee question, does not really put that hand to use, he or she would find it relatively difficult to modulate the muscles, especially when you tell them to perform certain tasks. We have this experience with several amputees. Some cannot even perform some tasks anymore, even though they still have some of the muscles there. Why? The reason is because they have not put those muscles to use over a long period of time. And one of the things for this study, no, we didn't investigate that. But in our previous study, yes, we did some pilot investigation. And part of the things we found out previously is that the level of the lengthier the period of amputation, the more challenging it becomes for those amputees relative to perform certain tasks. And this also you could see from their data when you analyze. You would notice somewhat more irregularities, even for the same class of movement across trials, compared to amputees who have just been amputated for a short period of time. You can see they have more regularities for the same task when they perform the same task. I don't know if I've been able to make that clear.
Yeah. So I suppose it's very important then that someone is fitted with a prosthetic, say, a short time afterwards in order to maintain that capability.
It's very important.
Thank you.
Ask the question. I'm happy to discuss it.
Yeah, so about the stroke victims, I was wondering if you've done or heard of any studies that compare between the EMG signals of stroke victims and non-stroke victims.
EMG signals and stroke victims.
Yeah, if the EMG signals change between someone who hasn't had a stroke and someone who has had a stroke.
Yes, I have read a paper. It does affect.
So probably the signal is reduced.
Somewhat in terms of quality. And one of the studies were actually not for this work. I talked about BCI also, brain-computer interface or brain-machine interface. There is one of my postdoc. I'm not directly supervising, but she's working with me as well. we're trying to look at in our project, we're trying to look at the affected side of the stroke patients and the intact part. And of course, but not this time around, not from EMG, but from EEG. And of course, the characteristics differ for both sides. So I think definitely it would affect.
Any other questions? Okay.